Welcome back. In this video, we are going to solve problem 5.50 that is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer Johnston, 6th edition. So statement is for the beam and loading shown, determine the equation of shear and bending moment curves and maximum absolute value of bending moment in beam, knowing that K is equal to 1 and K is 0.5. So you can see this is a cantilever beam having fixed support at this end, and there is a uniformly increasing load or triangular load on the upper portion where magnitude is W0 at this point, and there is a uniformly decreasing load having magnitude minus K into W0 at this end and 0 at this end. The total length is L. So you have to find the equations of shear and bending moment diagram, and then for maximum absolute value for K is equal to 1 and K is 0.5. So let's start with the solution. So what will be the first step? The first step is that if we cut this beam at any distance of X, so let this distance is X, clear, and the total length is L, so it means that this distance will be equal to L minus X. Now here the magnitude will be W1 and here the magnitude will be W2 at this points, and we will find the net W which is acting on that. So here you can see that if we have similar triangles over here, which is this one and this one, these are the two similar triangles. So if you take the ratio of their side, it will be same. So if I can write here W over entire length L will be equal to W1 over X. So from here what we will get is that we will get W1 will be equal to W0 into X divided by L. Okay, now for the lower portion you can see you have a triangular load. So what we will do is that we have one smaller right angle triangle is this one and the second one is this one. So we will take the ratio of their side. So from here you can see that this will be equal to minus K into W0 divided by whole length L will be equal to W2 divided by L minus X. And from here you will get this W2 will be equal to minus K into W0 into L minus X divided by L. Now we have this W1 and W2, so your net distributed load will be equal to W1 plus W2, and we can write it as W1 is W0 X divided by L plus W2 is minus K into W0 into L minus X divided by L. Okay, if you further simplify it, so what we will do is that we will take LCM, so it will be L and it will be W0 into X minus K into W0 into L minus X will be equal to W. Okay, so further simplifying it, it will be W0 into X minus K W0 into L plus K W0 into X divided by L. That will be W. Okay, further solving it, you can see that, that W0, if you take this W0 into X common, so one W0 into X is there and one W0 into X is there, so it will give you W0 into X. Here we will have 1 plus K, and that is minus K W0 into L divided by L. This will be W. Okay, and if you separate them, so it will be W0 into X into 1 plus K divided by L, and that will be minus K into W0. So this is the value of net W load that is acting on the beam. Now what we will do is that we know that this dV over dx is equal to minus W. So we will write the value of minus W. So it will be minus W0 into X into 1 plus K divided by L plus K0 K into W0. That will be dV over dx. And further if you write it, so it will be dV over dx is equal to K into W0 plus minus W0 into X into 1 plus K divided by L. Okay, what we will do is that we will integrate this, or we will multiply dx on both sides. So it will give us dV will be equal to K into W0 into dx minus W0 X into 1 plus K into dx divided by L. Integrate this equation, so you will get V on the left side, and that will be K into W0 X, and that will be minus W0 into 1 plus K into X squared divided by 2 plus C1, which will be the constant of integration. So let this will be your equation number 1. Now we know that okay, we can also find C1. So C1, for that we will use boundary condition, and I will show you to get it simplified. We use boundary conditions and to get C1. So what are the boundary condition is that at X is equal to 0, we have shear force is equal to 0. So you can see here at X is equal to 0 because W2 and W1 are function of X. So at X is equal to 0, shear force will be 0. So if you put in equation 1, so you will get this left side will be 0, this will be 0, and this will be also 0, and we will get C1 will be equal to 0. Okay, so put C1 in equation 1, so we will get V is equal to K into W0 X minus W naught into 1 plus K into X square over 2. And this is equation base A. So equation A is the shear force equation for shear force curve. Okay. Now what we will do is that we will move toward, as we know that dm over dx is equal to V. So from here we know that dm is equal to V into dx. So V is this one. So dm will be equal to K into W naught x minus W naught into 1 plus K into X square over 2 into dx. And if you integrate it, so we will get moment on the left side, and that will be K into W naught x square over 2, and that will be minus W naught into 1 plus K into X cube divided by 6. Plus there will be a constant of integration which will be C2, and we can find this C2 by using boundary condition. And that boundary condition is that at x is equal to 0 we have moment is equal to 0, because in cantilever beam the at free end moment will be equal to 0. Okay, so put in equation, and let this is equation number 2. So what you will get is that you can see this will be 0, this x due to x it will be 0, and this will be 0. So we will get C2 will be equal to 0. C2 is equal to 0. Now if you put C2 is equal to 0 in equation number 2, so you will get this moment equation will be equal to K into W naught x square over 2 minus W naught into 1 plus K into X cube over 6L. Okay, I think where we, okay, K. So I think I have made a mistake. You can see I have to check it from this. If you integrate it, you will get K, that K into W naught into X. Okay, you can see here we haven't written L, so you have to put L here. So this is L, and again this is L, and this will be L, so it will be 6L X cube. And this is your equation number B. So equation A and equation B are required shear and bending equations for shear force and bending moment curves, which is the answer of our first part. Now what we will do is that we will copy these two equations, and I will copy these two equations. So let me copy it. This is your equation number A. So I will copy it to the next page, and we will paste it over here. And similarly we will copy equation number B as well. So this is your equation number B. Paste it over here. Okay. Now remove these extra things. Okay. Now, as in part B, it is given that find the maximum absolute value of bending moment for K is equal to 1 and K is equal to 0.5. So what we will do is that first we will take for K is equal to 1. So if you take K is equal to 1, put in equation A. So what you will get is V is equal to W naught into X minus W naught into, this will be 1 plus 1 into X square over 2L. And from this we will get V is equal to W naught into X minus W naught into X square over L. So this is the shear force equation for K is equal to 1, and put K is equal to 1 in equation number B. So when you put it, so you will get moment will be equal to W naught X square over 2 minus W naught into 2 X cube by 6L. And from here we will get W naught X square over 2 minus W naught X cube over 3L. And that will be the second equation for equation of moment. So if you take LCM, so it will be 6L. So that will give you 3W naught X square minus W naught X cube. Okay. This will give you X cube. So this is your, this is your equation, bending moment equation for K is equal to 1. Now we have to find the maximum shear, maximum bending moment. So we know that at in cantilever beam at X is equal to L, we have maximum bending moment. So put X is equal to L in above equation. So we will get moment is equal to 3W naught L square minus W naught L cube divided by 6L. And that will give you 3W naught L square over L 6L minus W naught L cube over 6L. And from here we will get W naught L over 2, and from here minus W naught L square over 6. Welcome back. In this video, we are going to solve problem 5.51 that is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer Johnston, 6th edition. So statement is determine the equation of shear and bending moment curve for the beam and loading shown, and in part B, the maximum absolute value of bending moment in the beam. So you can see this is a simply supported beam AB having pin support at point A, and at point B we have a roller support, and there is a triangular load, or you can say linearly varying load of W is equal to W naught X over L, where W is a function of L, and you can see this is the direction of X. So wherever you want to find this W, so again that will be X, and at that point you can find this W, clear? And this W naught will be here. I will show you how. For example, if you are going to take it over here, so this is your X, clear, and here you have magnitude W, and you are going to find this W. So by using two similar triangle, one is this one and another one is this one, you can take the ratio of their side, that will be equal. So if I take W naught over L, that will be equal to W divided by X. So from here you will get this W will be equal to W naught X by L, which is the same. You can see this equation is same that we have derived here. Okay, now we have this W. So we know that this change of shear force with respect to X is equal to minus W. dV over dx is minus W. You know this equation very well. Okay, because this distributed load is 1 degree less than the shear force, or you can say the shear force will be 1 degree higher than this W. So this is the equation. So put the value of W in this equation. So that will be equal to minus W naught X by L. So you will have this equation dV over dx is equal to minus W naught X over L. So from here you will get this dV is equal to minus W naught X by L into dx. Now integrate it on both sides. So you will get integral of dV is equal to integral of minus W naught X over L into dx. So integral of dV will give you the shear force, and that shear force will be equal to minus W naught over L and integral of X into dx, which will give us minus W naught by L plus X square over 2, X square over 2, sorry, this is not plus, this is multiplied because integral is multiplied, X over 2 plus C1, which is constant of integration. So from here you will get this shear force is equal to minus W naught X square over 2L plus C1. So this is your equation number 1. Again, we know that this V is also equal to dm, change of bending moment with respect to X. This shear force equal to change of rate of change of bending moment with respect to X, because shear force is 1 degree less than the bending moment. So from here you can see dm will be equal to V into dx. So put the value of V, which is minus W naught X square over 2L plus C1 into dx. That will be dm. So if you integrate it on both sides, so integral of dm is equal to integral of minus W naught X square over 2L plus C1 into dx, and this integral of dm will give you bending moment, and that will be equal to minus W naught X square over 2L plus integral of C1 into dx, plus there is also a constant of integration C2. So from here we will get minus W naught X cube over 6L plus C1 into Xn plus C2. And this is the bending moment equation, and this equation is known as equation number 2. So you can see that both these equations having C1 and C2, they are unknown constant of integration. So C1 and C2 are unknown constant of integration, and we can find them using boundary conditions. We can find them C1 and C2. How we will find them? So you can see that the first boundary condition is that at X is equal to 0, you have moment is equal to 0. Let me show you here. You can see you have at X is equal to 0 because this is a pin support. So at X is equal to 0, here moment will be equal to 0. So you will put it in equation number 2. Put in equation number 2. So put in equation number 2. Okay, this is equation number 2. So when you put X is equal to 0 in this equation, so this will be 0 and this will be equal to 0, and moment is already 0 here. So it means that C2 is equal to C2 is equal to 0. So I will write C2 is equal to 0. Now what we will do is that we will use the second boundary condition, and second boundary condition is that at x is equal to L, you have moment is again 0. And you can see at point B you have roller support, and at this point x is equal to L, so moment will be also equal to 0. So again we will put in equation number 2. So it will be equal to m will be 0 minus W naught L cube over 6L plus C1 into L, and C2 is 0. So from here C1 into L will be equal to W naught L square over 6. So from this we will get C1 will be equal to W naught L by 6. Okay, so this is the value of C1 and C2. Okay, put the value of C1 in equation number 1. So which is the equation number 1? This is your equation number 1, which is minus W naught. So I will write it here, V is equal to minus W naught X square over 2L plus C1, which is W naught L by 6. Clear? And if you take this W naught common from this, W naught over 6 common from this, so what you will get is that W naught X square over 2L plus C1 is W naught L square over 6. So if you take this W naught, okay, let me simplify it further. So if you take the LCM, so it will be 6. Let me show you 6 and 2. 2 3s are 6 to 1. So it will be 3 1. So it will be 6L. Now 6L divided by 2L is 3. So 3 multiplied by minus W naught X square plus 6L divided by 6 will give you L. So it will be W naught L square. Okay. So further simplifying it, V will be equal to minus 3 W naught X square plus W naught L square over 6L. And if you take this W naught L square common from this, divide by 6L. So it will be minus 3 W naught, sorry, minus 3X square, minus 3X square plus L square. Sorry, what I have, take only W naught over 6L. Okay, wait. 3 W naught. Okay, what, I am making a mistake somewhere. So if you take this 6L and W naught common, so it will be W3 minus 3X square plus L square. Okay, L square. And from this you will get V is equal to W naught over 6L into L square minus 3X square. And this is your equation number 3, which is the required shear force equation. Now for bending moment equation, put C1 and C2 in equation number 2. So this is your equation number 2. Okay, this is your equation number 2. So after putting that, you will get M will be equal to minus W naught X cube over 6L plus C1, which is W naught L over 6 into X, and C2 is equal to 0. So from here you will get this equation, moment equation. And if again you take the LCM, so this moment will be equal to 6L, so minus W naught X cube plus W naught L square X. And from here we will take W naught over 6L common from that. So what we will get is minus X cube plus L square into X. Okay. So further simplifying it, this moment will be equal to, if L is multiplied to this inner two portions, so we will get W naught over 6 into minus X cube over L plus L square over L into X. And that will give us the moment is equal to W naught over 6 times L X minus X cube over L. And this is equation number 4. Now equation 3 and 4 are required. This is required shear force equation for the loading shown, and this is required bending moment equation for the loading shown. Now in part B we have been asked to define the maximum absolute value of bending moment. So we know that maximum bending moment occurs when where shear force is equal to 0. So put V is equal to 0 in equation number 3. What is equation number 3? Let me show you. This is your equation number 3. So if you put V is equal to 0, so this will be equal to 0 is equal to W naught over 6L. 0 is equal to W naught over 6L into L square minus 3X. L square minus 3X. So from here what we will get is 0 is equal to W naught L square W naught L square minus 3X, because when you multiply 6L on both sides, so 6L multiplied by 6L, this will give you 0 and it will cancel with this. So from here we will get 3x is equal to W naught L square, and we need x, the location where shear force is equal to 0. So it will be W naught L square over 3. Okay. I think, let me check it. Okay, this is, you can see, by moving here, I made a mistake. This is square. So I will make it square. It will be square. So 3x square, and this is also square. So if you find x, so x will be equal to, and one more thing is that, again, this W naught will be multiplied with this and with this. Here, W naught. Okay, so here I also have W naught. So W naught will cancel. So what I have to make this, it will be equal to x square is equal to L square over 3. And if you take square root on both sides, so it will be L square over 3, which will give you L by under root 3. X is equal to L over under root 3. Now this is the value of x for which the shear force will be 0 and bending moment will be maximum. So put x is equal to L by under root 3 in equation number 4. Equation number 4 is this one. This is your equation number 4. So let me write it. This is 1 over 6 W naught into Lx minus x cube over L. So I will write it, moment is equal to 1 over 6 times W naught into Lx minus x cube over L. So just plug in the value of this x in this. So when you put it, it will give you maximum bending moment. So it will be equal to 1 over 6 W naught into L multiplied by L over under root 3 minus L over under root 3 whole cube divided by L. Okay, yes. So what we will get is that 1 over 6 W naught, and it will be L square over under root 3, and that will be equal to minus this L and L. Here it is 1. So it will be L cube over cube whole cube divided by L. So simplifying it, this L will cancel with one of this. So it will be L square over under root 3 minus L square over under root 3 whole cube. 1 over 6 W naught. Okay, that is maximum bending moment. And further, if you simplify this, you take 1 over under root 3 and multiply it with L square, then minus 1 over under root 3 power 3. So that will give you, and divided by 6. So it will give you 0.0642 W naught L square, which is the maximum bending moment. And that is the answer of our second part. So this was all about this problem 5.51. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 5.52 that is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer and Johnston, 6th edition. So statement is determine the equation of shear and bending moment curves for the beam and loading shown, and in part B, the maximum absolute value of bending moment in the beam. So you can see this is simply supported beam AB having pin support at point A and roller support at point B. The total length of this beam is L, and along this longitudinal axis, it is represented by X. And you can see this, there is a distributed load, and the function for this distributed load is equal to W naught sine of pi x over L, where x is any length. So you can take the length along the longitudinal axis anywhere. This can be x, this can be x anywhere. So when you put the value of x over here in term of L, so you will get the distributed load at that length of x. So let's start with the solution. So for first step will be, as we know that we have been given W is equal to W naught sine of pi into x divided by L, and we know that this rate of change of shear force with respect to longitudinal axis is dV over dx, that is equal to minus W, and W is this one here. So you can just plug the value dV over dx is equal to minus W naught sine of pi x over L, and this dV will be equal to minus W naught sine of pi into x divided by L multiplied by dx. And if you integrate it on both sides, I will write it, integrate it on both sides, so you will get this V will be equal to integral of minus W naught sine of pi x over L into dx. So we will take minus W naught out of this, so we will left with integral of sine pi x over L into dx. Now you can see I have written the formula integral of sine A into x, where A is here, A is equal to pi by L. So it will be equal to, then V will become equal to minus W naught, and integral of this will give you minus 1 over, instead of A I will write pi over L, multiply by cos of pi x over L plus C1 there, and this will become equal to minus W naught minus minus, it will be plus. So W naught L over pi into cos of pi x over L plus C1. Okay, so do not, this will be like this. Okay, so this is your shear force equation. We call this equation as equation number 1. Now we also know that dm over dx is equal to shear force. Clear? And this dm will be equal to v into dx. So if you integrate it on both sides, so this will give you moment on the left side and integral of v into dx. So you can see you have value of v is w naught L over pi into cos of pi x over L plus C1 into dx. Okay, now you have to integrate it. So integral of w naught over pi into L cos of pi over L into x plus integral of C1 into dx. So this term, you can see the integral of cos of alpha into x, where a is here. You can also see it is pi over L. So I can write it w naught L over pi and multiply by cos of integral of cos of pi L will be equal to 1 over, instead of a I can write pi over L into sine of pi over L into x plus C2 and plus C1 into integral of C1 into dx is equal to C1 into x. So you will get moment will be equal to w naught L square over pi square into sine of pi x over L plus C1x plus C2. Now this is your equation number 2. Now C1 and C2 are unknown, constant of integration, and can be obtained by using boundary condition. So what are these boundary condition? I will show you now. Let me choose another color. The first boundary condition is that at x is equal to 0, you have moment is equal to 0. Why? Because you can see here x is equal to 0, so there is a pin support, so moment will be equal to 0. So put in equation number 2. So when you put x is equal to 0 in this one, so sine of 0 is again that will be 0. Clear? And C1x sine x is equal to 0, it will be also 0, and moment is 0, so it means that C2 will be equal to 0. So C2 is equal to 0. Okay, let me check it again. Sine of 0 is 0. Okay, now the second boundary condition is that at x is equal to L, we have again moment is equal to 0, because you can see here x is equal to L, there is a roller support, so at these conditions the moment will be 0 at this end. So put in equation number 2 again. So when you put x is equal to L, so it will be w naught L square over pi square into sine of pi into L divided by L plus C1 into L plus C2 is 0. So LL will cut and sine of pi is 0. So it means that this term will be equal to 0 plus C1 into L is equal to 0. So from here you will get C1 will be also equal to 0. Now what we will do is that put C1 in equation number 1. This is your equation number 1. So you will get V is equal to W naught L over pi into cos of pi x over L. And this is equation 3 is required shear force equation. Now for bending moment equation, put C1 and C2 in equation number 2. So it means that this is your equation number 2. So this moment will become equal to W naught L square over pi square sine of pi into x over L, and C1 and C2 are 0, so this will be 0. So we will have this equation, and this is equation number 4 is required equation for bending moment for the beam and loading shown above this. Now in part B we have to find the maximum absolute value of bending moment. So for that what we will do is that we know that for maximum absolute value of bending moment is obtained at location x, where shear force V is equal to 0. So put V is equal to 0 in equation number 3. So equation number 3 is this one. This one is your equation number 3. So I will write it over here. V is equal to W naught L over pi into cos of pi x over L. So if you put V is equal to 0, so W naught L over pi into cos of pi x over L. Now you can see the multiplication of these two terms will give you 0. So it means that for x is equal to L by 2, if you put x is equal to L by 2 over here, so this will be equal to W naught L over pi cos of pi multiplied by L divided by 2L, and this L will cancel, so we will left with W naught L over pi cos of pi by 2, and cos of pi by 2 is equal to 0. So means that this equation will be valid. This will be valid for x is equal to L by 2. So at this x is equal to L by 2, we will have shear force will be equal to 0. Now put this x is equal to L by 2 in equation number 4, which is the bending moment equation. So this is your fourth equation. I will write the equation moment is equal to W naught L square over pi square into sine of pi x over L. So put x is equal to L by 2, so moment will be equal to W naught L square over pi square and sine of pi L over 2L, and L will cancel, so we will left moment will be equal to W naught L square over pi square into sine of pi by 2, and we know that sine of pi by 2 is equal to 1. So this equation will be equal to maximum bending absolute value of bending moment, and that will be equal to W naught L square over pi square, which is the answer of our second part. So this was all about this problem 5.52. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.